So I believe we are live now, and it's my pleasure to start a new statistics department seminar from UFMG. Our guest today is Tamara Broderick. I'm pretty sure most of you know her. She's a young statistician, but she has been doing a lot of contributions in, Bayesian machine learning. She was a Michael Jordan. Michael Jordan is a successful name. People know that by now. From Berkeley PhD, and she's a MIT faculty now. She has plenty of awards, as you saw in her bio. I sent that to everyone. So I was super happy when she promptly said yes to us. For us, it's really important to see people that is so active, making the difference. We know every day, small steps and contributing to the progress of science, and such an active women working, and she was willing to talk with us without thinking. So thank you very much, Tamara, for that. Yes, for us was really happy to have you here. I know not in person, but hopefully sometime you can come to Belo Horizonte in Brazil to meet the department, see the structure of the city and the university and so on. So we are very happy to have you. The floor is all yours. You have 45 to 50 minutes to do your talk, and feel free to say whatever you feel like, and then start your talk. Okay.
Great, thank you so much. Thanks for listening to me today and joining me on this. So I'll go ahead and launch in. One thing I'll say is, if anybody wants to ask questions along the way, I'm super open to that. No pressure, but if you have any, I'm happy to take them. So today I'm going to be talking about a check that you can run on your data analysis, namely a check to see if there exists a super tiny fraction of your data that, if you dropped it, would change your substantive conclusions. Before I go on, I'll just mention that this work was done with an amazing group. My postdoc, who's about to finish his postdoc, Ryan Giordano, and he's going to start a faculty position at UC Berkeley in statistics, and our incredible collaborator, Rachel Meager, who's definitely the economics expert on this paper, and is a professor at the London School of Economics. Okay, so at a high level, today's talk is about when can I trust decisions that I'm making from data. And so, in some sense, the promise of the past few decades has been that as we get more data and better computation, data analyses can increasingly drive life-changing decisions. And we sort of hope that they'll help us make good decisions. But as part of that, we probably want to really check that they're doing the right thing. If we're making decisions in personal finance, in medical care, in education, these are areas that really matter to us. We really want to make sure that we're getting it right. Now, I'm not going to be exhaustive today. I'm not going to talk about all the possible checks that we can and should run on data analyses. Rather, I'm going to suggest a particular check that might often be useful. And it's going to be sort of inspired by the observation that a typical setup that we have in a data analysis is that we run some data analysis on an available set of data, we reach a decision, and then the whole point is to apply that decision to future data. So let me just give you a concrete example. Economists have run randomized controlled trials of microcredit, these small loans to individuals in impoverished areas. And the hope is to understand, is microcredit helping people? And if it is, to now invest in microcredit at future times in different locations, potentially. Well, an observation here is that we're generalizing from this first data set to this implicit second data set, where we apply the microcredit in the future. And we might worry about that generalization step if it turned out a super tiny subset of our data was absolutely instrumental to the original analysis. So I'm going to give you a concrete example, and then we're going to get into it in a lot more detail later in the talk. But in a real randomized controlled study of microcredit with over 16,500 data points, we find that we can drop one data point. We're not changing its value, we're just dropping it. And we can flip the sign of the effect. That's the difference between microcredit helping people and microcredit hurting people. And so I think we think in this case that maybe we're a little bit worried that this is sort of a fragile conclusion, that we maybe would like to gather more information or really dig in deep before we invest in microcredit in a new location, if this was all we knew. And so the observation that we want to make is we would like to know if there was this super tiny subset of our data in a data analysis. And so the challenge with knowing that, and the reason that we're sort of having this talk and discussion today, is that it turns out it's just absolutely impossible that you could actually drop every tiny data subset and check, did you change your substantive conclusions? We'll get into a lot more detail on that just from a computational standpoint. And so today we're going to see that we can take an approximation instead. And that approximation is going to be fast. It's going to be automatable, so the user doesn't have to put in a lot of work. And we're going to have various support for its accuracy. In particular, we're going to give an empirical and a theoretical analysis of how this approximation behaves, its accuracy, what is it doing, what is it showing us, stuff like that. Okay. So in the rest of the talk, first I'm going to talk in a little bit more detail about why do we care about this particular form of robustness to dropping sort of the worst case tiny subset of data. I'll talk about how we would like to find this worst case tiny subset of data to drop, but we can't because it's totally computationally just astronomically expensive. We're going to see that we have this fast and automatic approximation. And once we have the approximation, we can check that many analyses are robust in the sense that I'm describing, but many are not. And that this type of robustness isn't just the same as other types of robustness that you may well be familiar with from other types of statistics. So this one isn't just a product of gross outliers. It's not something that you're going to avoid just by checking whether you have a large p-value. It's not just a product of heavy tails, et cetera. We'll start to get some intuition that what it's really reflecting is a notion of signal to noise in the data, where for the moment, signal is roughly the amount of information about what we care about, and noise is sort of the error that's making it hard for us to access that information, but we'll get into a lot more detail shortly. Okay, so let's focus on when do we care about dropping this worst case tiny data subset. Well, a first observation is that any useful data analysis has to be sensitive to some change in the data. I think sort of unfortunately, when we talk about sensitivity or robustness, it's often as though they're monoliths, like you're either sensitive or you're not, you're robust or you're not. But of course, what we really mean is always some sort of shorthand. We really mean sensitivity to some change. And so the question isn't, is an analysis sensitive? It's what types of sensitivity are concerning to us? What types of sensitivity are worrying to us? And of course, that's going to vary by problem. There's probably multiple types of sensitivity that we should be concerned about. But here, again, I want to suggest to you just one type that we think is often concerning. In order to dig into that, we're going to be looking at economics a lot in this talk. Why economics? It's got super important applications that absolutely affect all of our lives. Man, is it an amazingly reproducible field. This is going to be a real theme of this talk, and that's really just what has made this work even possible. And we got to work with an amazing economics expert in Professor Rachel Meager, and so that was just really fun for us. Okay, so just as one illustrative example that is not all-encompassing, but is a nice cartoon, imagine we had an intervention that affected only a few people. So maybe we do our randomized controlled trial of microcredit. So this village receives microcredit and this village does not receive microcredit. And we have to measure some notion of efficacy. Maybe it's something like business profit between the two businesses. And a typical thing that economists will do is they'll compare averages. So look at the mean business profit in this village and the mean business profit in this village, and they'll ask, are they different? And in particular, maybe it's the case that right before they measured the mean business profit, a couple of CEOs from Amazon and Microsoft walked into this village. And so now, because their business profit is so high, the mean business profit in this village is going to be through the roof. And it's going to look like microcredit is amazing. And the reason that we sort of wouldn't trust this result is, well, we don't think that every set of villages that comes along is going to have these CEOs in them. And so we think that it would be nice if we could remove this tiny fraction of data and then see, well, what's the result with the data that's left? And does that change things a lot? Okay, So in this case, we'd like to remove a tiny fraction of data and see if that changes our conclusions. Of course, this is cartoon. We don't expect CEOs to walk into our villages, but a very real concern is that some tiny fraction of people are actually benefiting from microcredit and the rest are not, and we would like to detect that. Now, in general, there are plenty of standard statistical tools to try to address this notion of generalization, that, if we come to a conclusion on a particular data set, can we trust it on a new data set? But typically they make some assumptions that I think we wouldn't be comfortable with in practice and could really make a difference. So one, typically they assume that our new set of data is IID, independent identically distributed, from the same distribution as our original set of data. And we know this isn't true. We know that in general, if only because time has passed, the people in a village are different than the original people in the village who were measured as part of the original study, but also very likely we want to apply, microcredit at a different location. And so the place where the policy is meant to be applied, the decision is meant to be applied, is typically going to be different from the actual analyzed population, and in systematic ways. Of course, these methods assume that we have a correct model, typically, a correct likelihood, and we know that that's not true. We know that models are always misspecified. Typically, these methods are going to assume that the output is what we actually care about. And of course, that's generally not true. We're reporting a convenient proxy. For instance, in the case of microcredit, we actually want to know that many people are being raised out of poverty, and we know that a statistical mean, an average, is not going to actually reflect that exactly. But it's a convenient proxy, and it's what people are using. Often in the social sciences, it's assumed that data is missing at random, but we know that in fact, small fractions of data, when, for instance, a survey happens, or people are following a cohort, small fractions of data are absolutely missing, not at random. And so in all of these cases, these realistic cases in real life, we'd be concerned if dropping a very tiny fraction of data changed our conclusions, because it suggests that the assumptions of the standard tools aren't, good enough. Okay, I want to emphasize that these concerns are not specific to economics. Economics is what we'll be looking at today, but certainly in general, we expect that we're trying to find some decision or some general truth about science or, social science or engineering, and we'd like to apply it in a future time and place. Our models are always misspecified. We're typically reporting a convenient proxy. The missingness not at random might be something that we often see more in the social sciences than other areas, but certainly it's a general concern. And then finally, I'll note there are plenty of cases where this type of robustness should not bother you, but then you should be upfront about it. And so, for instance, suppose that I was studying some kind of rare crime between two cities. Each city had 100,000 people, and maybe there were 6 instances of the crime in this city and 3 instances of the crime in this city. Well, I wouldn't want to remove a tiny fraction of my full 200,000 people, because then I'm just going to remove all the crimes that I was studying. But conversely, I should probably be upfront that really, for the purposes of comparing the two cities, I have 9 data points, not 200,000. Okay, so hopefully at this point, you care about this particular type of robustness, this idea of, is there a super tiny fraction of data, this worst case fraction of data, that if I dropped it, I could change my substantive conclusions? And so with that in mind, let's start establishing a little bit more notation, a little bit of nomenclature. So we're going to say we might worry if removing a very small fraction of data changed our decision. And we'll call that small fraction alpha. Now, because it's a fraction, it's between 0 and 1, but we'll be really worried if it's very tiny. Again, we don't really worry if some changes our data analysis. Eventually, we think that that should happen with a big change. It's only if it's a small change that we're really worried. What does it mean to change our decision? Well, it depends on what we're doing in the analysis, but let me give you a few examples. Maybe we'll invest in microcredit if we estimate that the effect of microcredit is positive, that it's helping people. And so we would be concerned and we would change our decision if we could change the sign of that estimated effect. Maybe we would invest in microcredit if we found a statistically significant effect, in which case our decision would change if we changed that statistical significance. Maybe we're not going to invest in microcredit right now, but if we could get a positive effect that was statistically significant, we would. And so then we would change our decision if we could change to a significant result, a statistically significant result of the opposite sign. Okay, so with that in mind, we're going to define some new ideas. We're going to call it the maximum influence perturbation. That'll be our name for the largest possible change in some quantity of interest that we can get by dropping our alpha fraction of the data. So for instance, if we're interested in the effect size, we'll say, what's the biggest change in the effect size that we can get by dropping at most 100 alpha% of the data? And usually we're thinking of this directionally. So if we're interested in changing the sign and the effect is currently positive, we'll say, how negative can we make it? Or how close can we get it to 0 by making this change? The most influential set, once we have the maximum influence perturbation, we probably want to know what are those data points that we dropped to achieve the maximum influence perturbation, so we can look at them, we can plot them, we can see what's going on. And so we'll call that the most influential set. Okay, so at this point, we have the thing we'd like to compute. We'd like to compute this maximum influence perturbation or something along those lines. And so how could we do that? Well, a straightforward idea, at least, is to try brute force computation. How about we take every possible tiny data subset, drop the data subset, and rerun the data analysis with that data dropped. So let's think about what would be involved computationally to do this. Well, suppose we have 16,000 data points. We've already seen, in some sense, a data set with over 16,000 data points. Suppose we decided that we would be concerned if we could drop 0.1% of our data, super tiny fraction, and change our substantive conclusions. Well, a data set of size 16,000 has about 10 to the 53 different subsets of size 16. And that's not even including the subsets of size 15 or 14 and so on, which are even smaller. So if our data analysis takes 1 second, and if you've run a data analysis, you realize this might be optimistic. But if it takes just 1 second to run, then this check takes over 10 to the 46 years to run. There are a lot of problems these days where people say, man, if you just had the parallel computing of Amazon or Facebook or one of these big tech companies, you could solve a problem. That's not true here. You could have all the parallel computing of all the major tech companies, and that's still not going to save you. You're still not going to be able to solve this computational problem. And so it seems like we need something else. And that's where this approximation is going to come in. We're going to approximate the effect of dropping this very small subset of data. Okay, before I show you the approximation, let's actually see it in action on a real data set. And in particular, that's going to be this data set that we mentioned at the beginning. So this is from Angelucci et al. 2015, a really awesome paper that there were 7 very famous randomized controlled trials examining the effect of microcredit. Each one's in a different country in economics. And this is the largest of them with 16,561 households. You can think of them as small businesses for the purposes of our discussion right now. I can't emphasize enough the fantastic reproducibility and data sharing of this paper and economics in general. We were able to reproduce everything to multiple decimal places from the original paper. Okay, so my understanding from the economists is that there are more complex models with more covariates that people can run, and the major conclusions look pretty similar to the simple model. So let's look at the simple model. If a simple model can be non-robust, surely a more complex model can be non-robust. So here we have a very straightforward linear regression. There is a single covariate. So N is indexing the households or the small businesses here. XN is the microcredit indicator. We know in the randomized controlled trial whether or not this small business received microcredit. So it's 1 if it received microcredit, it's 0 if it did not. YN is the business profit of this small business. So if it's positive, it's having a positive business profit. If it's negative, it's having a negative business profit. Theta naught and theta 1 are the parameters, the unknowns. So theta naught is effectively telling us what's the business profit if microcredit didn't exist. And theta 1 is the microcredit effect. How much is microcredit helping, if at all? If theta 1 is positive, it is helping. If theta 1 is negative, it is hurting. Okay, so the original paper found, and we corroborated, that theta 1 hat, using just a simple OLS estimator, is negative 4.55 US dollars purchasing power parity per 2 weeks with a standard error of 5.88. So we can use our approximation to see if we could change this by dropping a very small fraction of data. The first observation is our approximation takes 2 seconds to run, not 10 to the 46 years. So we actually can run this approximation. The next observation is we can remove 1 household and change the sign of the effect from negative to positive. But you're probably thinking, hey, this wasn't statistically significant to begin with. That negative 4.55 is within the standard error. And so I'm not sure this would actually change my decision. But we can remove 15 data points. So 15 data points is still less than 0.1% of the entire data set here. Very, very, very small fraction of data. And we can get a statistically significant result of the opposite sign. This is arguably a case where the substantive decision has changed. We would change whether we invest in microcredit in this case. Now, I think importantly, there's no reason for you to trust our approximation at this point. I haven't told you the approximation. I haven't told you anything to support it. But what I can tell you is that we're going to tell you that most influential set. We're going to say, here are the data points that we dropped to achieve the change, the purported change. And so you don't have to trust us. You can just run directly without those data points at the cost of one additional data analysis. So now you're just taking 2 data analyses of cost instead of 10 to the 53 data analyses, and check directly. And in fact, that's what we do here. And we find that we can, in fact, achieve these changes. It's not just the approximation giving us bad information. Okay, I think there's a lot of really natural questions that you could have at this point. One, you might be thinking, hey, this wasn't a statistically significant result to begin with. Maybe that's the problem. We're going to see later that it's not that. That statistical non-significance is not decisive. In both real data analyses and simulated data analyses for intuition, we can see that we can, in fact, change this very small fraction of data sometimes. You might be thinking the problem is gross outliers. We're going to see later that that is not decisive either. We can have data analyses with no gross outliers and still get these changes with by dropping a very small fraction of data. You might be familiar with other types of robustness. So maybe you're thinking the problem is heavy tails or reporting means, and we're going to see that those are not decisive either. If you have done Bayesian analyses, as I have, you might be thinking, hey, maybe if you were Bayesian, you wouldn't have this problem. And we're going to see, I think we won't get into a ton of detail today, but we'll see a result that is not decisive on a real data analysis. Okay, so we've seen this in action at this point. Oh, and hopefully we'll get some intuition about what really is going on, that this is reflecting a notion of signal to noise in the data, that we're going to see that data analyses tend to be robust when signal to noise is high and non-robust when signal to noise is low. Okay, so at this point, we've talked about why do we care about finding this worst case small subset of data that if I dropped it could change my substantive conclusions, trying to see if that exists. We talked about how we'd like to check for this if we had infinite computational power, and we don't. And so we find that it's too computationally expensive. We need an approximation. And hopefully at this point, you're wondering, what is that approximation now that we've seen it in action? And that's what we're going to do next. Okay. So in order to talk about our approximation, first, let's set up a pretty generic looking data analysis. So again, N is going to index our data points. Dn is going to be our nth data point. For instance, if I were doing a supervised learning problem, it could be that xn are my covariates and yn is my response or set of responses. I don't have to be doing supervised learning, though. This could be a generic data point. It could be for semi-supervised learning. It could be for unsupervised learning. That's all fine. Now, in a pretty typical data analysis, I'll have some parameters, some unknowns. Let's call those theta. We saw an example of this in the microcredit example just a moment ago. We had theta naught and theta 1. And we have some loss that relates our parameters to our data points. And we might solve for theta. We might estimate theta by taking the sum of the losses over capital N data points, perhaps having some kind of penalty on theta, and then minimizing this penalized loss over theta. And so we'll call our estimator theta hat that results here. Okay, so lots of familiar things take this form. Anything that's a loss minimization problem. So OLS, any kind of maximum likelihood estimator. Once you allow this penalty, you could have a maximum a posteriori estimator. It turns out variational Bayes fits into this form. Tons of things fit this form. Actually, it turns out that our method works with any Z estimator. So where you take some estimating equation and set it to 0. I'm just going to focus on this particular minimization problem because I think it's very familiar. And we'll often solve it by setting a gradient to 0, but there's actually this more general formulation. Okay, now things don't end there. So you'll recall from the microcredit example we just saw that it's not like we just estimated all the theta hats and then we were good. We actually used some aspect of the theta hats to make a decision. And so we're going to call that our quantity of interest, sort of our decision-making quantity. So for instance, in the microcredit case, we took one of the theta hats to make our decision. We said, actually, the one we really care about is theta hat 1, the microcredit effect. And so in that case, we're picking out a particular element, let's call it the pth element of theta hat, and we look at its sign. If we were looking at something like statistical significance, we'd look at theta hat plus or minus 2 standard errors. But we could also look at a posterior mean or a posterior credible interval endpoint if we were doing Bayesian inference. The point is we just take some summary. It's typically going to be one-dimensional at the end of the day, and we make a decision with it, and that'll be fine. Okay, so everything up to this point is hopefully a review from your statistics classes. And now we're going to change things just a little bit. We're going to start giving every data point a weight. So data point 1 gets a weight of size W1, data point 2 gets a weight of size W2, et cetera, up to W sub capital N for our capital N data points. And we can think of our original data problem as having every weight be size 1. So we can collect those all in the all ones vector. Let's call it 1 sub capital N. And we can conceptualize dropping a data point as taking the corresponding weight from 1 to 0. So if we drop the 10th data point, we take W10 from 1 to 0. If we drop the 10th and the 11th data point, we take both of those weights from 1 to 0. And so hopefully you agree with me that every drop data subset is in one-to-one correspondence with a different W vector. And so now we can ask, how is this going to change our data analysis up top? Well, we're just going to pre-multiply each of our losses by the corresponding weight. And so why does this make sense? Well, if the weight is 1, we're including the loss for that data point. If the weight is 0, we're getting rid of the loss for that data point. We're removing that data point from the analysis. And so implicitly now, theta hat is a function of W, the W vector, which encodes which data points are dropped. And so our quantity of interest has to be a function of W. Either just because theta hat is a function of W, and so now phi is a function of W, or phi could depend on W in other ways, for instance, via standard error. Okay, so our next observation is that we're only concerned if we can drop a teeny tiny fraction of data and change our substantive conclusions. And so we're only concerned if we can change W a very tiny amount, just a few ones become zeros, and we can change our substantive conclusions. And so what we really want is we want to approximate what happens at phi when W changes very, very little. And so the observation here is, well, if we're changing the input to phi very little, maybe we can approximate phi pretty well with the Taylor expansion. What's the simplest non-trivial Taylor expansion? A first-order Taylor expansion. And so that's literally going to be the approximation. It's going to be a first-order Taylor expansion. And now I'm just going to spend some time writing that out and walking through it. Okay, so here we just have our generic data analysis up top at the end, just repeated from the previous slide. We have our quantity of interest, phi, from the previous slide, and an example quantity of interest. And so the idea is, hey, the all ones vector represents the original data analysis. We're gonna run that data analysis anyway. Let's do a first order Taylor expansion around that all ones vector. And so let me walk through what we're seeing here. Well, first, at the far left, we have phi of W. This is exactly what we would get from dropping the data points that correspond to the weight vector W. We wish we could compute this, but then we'd have to do those 10 to the 53 different calculations. It would be really hard to compute it for all the different 10 to the 53 different W's. We can't do that. And so we're going to use an approximation instead. Our approximation is going to be a linear approximation because it's a first order Taylor expansion. And so we'll call it phi super lin. Now we're just writing out the first order Taylor expansion. So it has the 0th order term, phi of the all ones vector. This is the original data analysis. You kind of have a sunk cost. You got to run at least one data analysis. But now, instead of repeating the data analysis 10 to the 53 times, we're going to use this first order Taylor expansion. So now we have the first order term in the Taylor expansion, which is effectively a dot product between W minus the all ones vector, and the first derivatives, psi. So these are just the first derivatives of phi with respect to W, the all ones vector. If you're familiar with influence functions, you might recognize this as the influence score of the nth data point. If you're not, don't worry, because it's still just a first order Taylor expansion. Now, that being said, there are a lot of really cool connections to influence functions. So for instance, even back in the 60s and like many decades ago, various people have noted that the influence score can be computed in basically some pretty straightforward ways via the implicit function theorem and the chain rule. Now, nowadays, we can take advantage of that and automate this computation. So the point is we can still use the implicit function and then the chain rule to express this influence score, because otherwise we're not really sure how we'd compute the influence score, but we can express it in terms of things like the derivative of f with respect to theta. And then those derivatives, you don't want somebody to have to sit down and write them out. And sort of, many decades ago, people thought that's what you'd have to do. But nowadays, you can use modern automatic differentiation tools. There's this really great overview, if you're not familiar with automatic differentiation tools, by Baden et al. In 2018. It's really revolutionized a lot of statistics and machine learning in the past couple of decades, just having them built into modern probabilistic programming languages and standard programming tools. But the main point here is that the user doesn't have to do any calculations. They just have to say, here's my loss, and here's my data. Now, implicitly, that loss does have to have a certain amount of differentiability. We do need to be able to take the derivative of f with respect to theta. But besides that, this is very automated. They don't have to do any calculations. Now, many authors have approximated or suggested removing some data points using an influence function. So for instance, if you look back in the older statistics literature, removing some data and approximating that using an influence function has been suggested as a tool for debiasing an estimate. That was sort of the hot thing back in the day, was unbiased estimation. More recently in the machine learning literature, it's been used as a tool for interpreting black box predictions. And we've done some work in a sort of like burgeoning subfield of approximating cross-validation using this idea. But to the best of our knowledge, nobody has empirically or theoretically analyzed dropping this worst case small fraction of data, this maximum influence perturbation that I described today. So those are all for pretty different use cases. I'll note that this work can also be seen as a special case of a breakdown point or local robustness. So just in the sense that like something breaks down when you remove this small fraction of data, although removal of data isn't something that the breakdown point literature has typically looked at. We actually got into this area by studying local robustness. So we actually were looking at things like if you change your likelihood or your prior slightly, how would that change your substantive conclusions and Bayesian analysis? But the same ideas can be applied here for dropping data. Something you might be thinking is, why stop at first order Taylor expansion? Why not try a higher order Taylor expansion? We have plenty of reason to believe that higher order Taylor expansions are going to be more accurate. But it turns out for some cases, for different types of applications of dropping data, this can be pretty useful. And we have some very early work on the archive on that idea. But for this application, for finding this worst case subset of data that if you dropped it would change your substantive conclusions, it turns out it's pretty important that we did a first order Taylor expansion. And the reason for that will become clear in a moment, because at this point, we actually haven't totally solved the problem. So if we go up to this equation, further up the slide again, we've replaced our 10 to the 53 different data analyses. We don't have to compute phi of W for 10 to the 53 different drop data subsets for 10 to the 53 different W values. But on the face of it, while we only have to do one data analysis to compute phi of the all ones vector, we still have to compute the linear approximation 10 to the 53 times. And from a computational perspective, we don't even want to do addition 10 to the 53 times. That's still too many times. And so let's think a little bit more about what's going on here. Okay, so we still have our first order Taylor expansion, still repeating just the top 3 lines from the previous slide. But now I want to make the observation that at the end of the day, what we want is we want to find the worst case exact change. So for instance, if we're trying to change the sign of phi, to go from positive to negative, then that implies that there's a particular direction that we're changing this, this phi. And I want to note, while I'm noting this particular directionality here, if we cared about the other direction, that's easy. We just make it negative phi. So without loss of generality, let's just say we're trying to find the biggest change, phi of w minus phi of the all ones vector. Now, what we're saying we're going to do is instead of using phi of w for all of those 10 to the 53 drop data subsets w, we're going to use the linear approximation instead. Well, once we've put the linear approximation in here, we can actually write an equation for this difference just using the Taylor expansion above. So in particular, it's like we just took phi of the all ones vector from one side to the other, and we're left with this first order term. There's sort of two options in the first order term. Either wn equals 0, in which case we get negative of the influence score, or wn equals 1, in which case that whole term disappears. Okay, now this suggests an algorithm to find the worst case w. And the algorithm is the following. First, number 1, compute the influence scores, these psi of n's. That's going to be a linear time cost. We just compute that psi of n for each n. So linear time and the amount of data. 2, sort the influence scores. So in general, when we sort our influence scores, that's going to be an n log n cost for n data points. So that's a little bit higher than linear, but if sort is the bottleneck in your data analysis, I'd love to chat with you. That sounds like a very cool data analysis. That is certainly not the case for the ones we're talking about today. 3, start removing the largest influence scores. So when we remove the largest influence score, we now have the worst case approximate change that we can get by removing one data point. Now, if we remove the second largest influence score next, we now have the worst case approximate change we can get by removing 2 data points. If we remove the third largest influence score, we now have the worst case approximate change that we can get by removing 3 data points. And so in general, we said we wanted to find the maximum influence perturbation. What's the largest change in our quantity of interest, phi, that we can get by dropping at most alpha fraction of the data? And so now we're going to be reporting the approximate maximum influence perturbation. We're going to keep dropping the worst influence scores, the largest influence scores, until we've dropped at most 100 alpha% of the entire data set. And then we're going to report what was the biggest change in the quantity of interest that we got, or what is the change in the quantity of interest that we got. And along the way, we can remember which data indices did we drop as we were going along, and that will be our approximate most influential set, the data that we dropped to achieve the approximate maximum influence perturbation. Okay, so this is the approximation. This is the approximation that I illustrated in the example from before. And so now we're going to spend a little time developing some intuition about this. In particular, first, we're going to look at some simulated data, because then we control everything about the data. We know what's ground truth. We know what's happening. And then we're going to look at some more real data analyses from economics. Okay, so let's start with our simulated data to understand what makes an analysis non-robust according to this type of non-robustness. In order to do that, we're going to look at a really simple model, again, so we can visualize it, so we have a lot of intuition already going in, because if I look at a more complex model, we don't necessarily have the same geometric intuition, but I think in a linear model with Gaussian noise, we all have a lot of intuition. And so we're going to have just a simple one-dimensional linear model. Again, n is indexing our data points. Xn is our single covariate. Theta is our one-dimensional parameter, and yn is our one-dimensional response. We're simulating our data, so we're going to simulate our noise. Let's have our noise be normally distributed with a variance of sigma squared epsilon. We're simulating our data, so we have to simulate our covariates, xn. Let's have them be normally distributed with their own variance, sigma x squared. And we're simulating our data, so we have to choose theta. So we're going to choose theta to be 0.5. Now we have to have some kind of decision criterion and data set. So we're going to say we're going to have 5,000 data points, and our decision criterion is going to be based on the sign of theta hat. And so we'll say, hey, if we have a particular theta hat that we observed, can we flip the sign of theta hat? Can we change our decision by dropping some of the 5,000 data points? Now, I told you very early in this talk that essentially what was going to be driving whether something was robust or non-robust under the methodology that I'm describing here is going to be a notion of signal to noise. So what do I mean by signal to noise in a little bit more detail? The signal is essentially the strength of the effect. In particular, in this case, we're trying to change the sign. So we have to make a change, or let's call it delta, of size theta hat to get from theta hat to 0. And so the delta here is just going to be the size of theta hat. The intuition here is that if theta hat is large, it's easier to detect the sign. And if theta hat is small, it's easier to mistake the sign. Now, we'll get into more detail later about what exactly noise is. It'll turn out that it's natural to think of it as an estimate of the scaled asymptotic standard deviation of our quantity of interest. But in this particular case, in linear regression, it takes a really nice form. It's about equal to sigma epsilon over sigma x. Let's talk about why that makes sense. If sigma x is really big and sigma epsilon is really small, this is a super obvious problem. You and all your friends are going to say exactly what theta is. There's going to be no discussion or uncertainty about what theta is. We can all tell what theta is just by looking at the problem. Whereas if I have the exact same theta, but sigma epsilon is really huge and sigma x is really small, note the changed size of the x-axis here, then it's really hard to tell what theta is. It's really difficult. The noise is swamping the signal here. And so in general, we think that we should have an easy problem and a robust problem when signal to noise is very high, and a hard problem and a non-robust problem when signal to noise is very low. Let's see if our form of non-robustness is detecting that. Okay, so what I'm showing here is on the horizontal axis, we're changing sigma epsilon in the problem. On the vertical axis, we're changing sigma x in the problem. And so in this lower right corner, sigma epsilon is very large, sigma x is very small. The noise is humongous. Whereas in the upper left, sigma epsilon is very small, sigma x is very large. The noise is much smaller. Now, what we're showing in the color is what percent of data can we drop to change our substantive conclusion, to flip the sign of theta hat by dropping some of our 5,000 data points. When the noise is super high, we see that we can drop an extremely small fraction of data and flip that sign. But as the noise decreases, or as the signal to noise increases, we find that it takes more and more data to be dropped to change the sign. And eventually we get to an area where there's so much data we have to drop to change the sign that the approximation itself becomes dubious. So that's what these little x's are. And eventually we get to a point where the approximation is dubious and we can't even find any data to flip the sign. That's what the gray represents. But that approximation only becomes dubious when W is very, very far from the all ones vector, when we have to drop a lot of data. And so the observation here is that we can detect if dropping a very small fraction of data suffices to change the conclusions, we can make that decision. And if it turns out that we can drop a very small fraction of data to change the conclusions, then we can say how small. So things break down precisely when we don't care about them anymore. Now, the other observation here is that we're seeing that the type of sensitivity that I'm discussing here tracks the signal to noise ratio. It's reflecting the signal to noise ratio. And we're going to see some theory later on that gives us a general sense that we kind of expect this. And this is just a particular case where I think, again, we have a lot of geometric intuition, so we can see kind of like why this is going on. Okay, I also want to point out here that other types of things that you might think would be decisive in other cases aren't. So while I said that misspecification can be concerning for this type of non-robustness and a reason we should care about it, it's not decisive. It's not the thing that it is detecting. In particular, this is a case where everything is perfectly specified. Because we generated the data ourselves, everything is well specified, and we're still seeing cases that are both robust or non-robust. Now, again, you might be familiar with other types of non-robustness where just reporting a mean or having heavy tails in the distribution are what tell you whether things are robust or non-robust. And here we're seeing that's not the case. These are cases where we're always reporting a mean. There are no heavy tails in the distribution, and we're seeing cases that are robust and non-robust. And again, you might be thinking, hey, maybe the problem here is gross outliers, but these are cases where we don't expect to have gross outliers in general, and we're still seeing robustness or non-robustness. So again, these are just not decisive. They can still influence what's going on, but not be decisive. Okay, so let's talk about some real data analyses. So now that we've talked about these simulated data analyses, in particular, I want to emphasize before going in that these are all awesomely reproducible. I think there's so much that we can all learn from the economics field. I think that's really amazing. Is there a question or?
Not yet.
Oh, okay.
But I have plenty of questions, but I will wait to the end.
Great, awesome. I just wanted to check. Okay, sweet. So first, let's see a real data analysis that illustrates that it's not just non-significance. So earlier we saw this example where we started with a non-statistically significant result, and you might be thinking maybe that's the problem and we can detect things with the usual p-values, but here we're going to see that's not the case. So very famously, there was this Oregon Medicaid experiment in the US. And so it has its own Wikipedia page. There's a lot of information of it out there, but basically there was a lottery in Oregon, a state in the United States. And in the United States, people are not guaranteed healthcare. And so the winners of this lottery could sign up for healthcare, which I think sounds very weird outside of the United States, but it's a thing that happened. And so Finkelstein et al. In 2012 looked at this natural experiment to see the effect of essentially either the lottery on healthcare the lottery on health or getting the healthcare directly on health. For their data, they had over 21,000 data points. These are survey responders, so we might already be concerned about things like missingness not at random. And there were many things that were studied in this analysis, and we reproduce them and study them in our own paper, but I'm just going to point out one here. So one thing that they found was a p-value less than 0.01 for a positive effect of a lottery win on health. So that's a statistically significant result. That's the kind of thing that makes the news. But we do find in this case that we can drop 10 data points, so that's 0.05% of the data, and change that statistical significance. And so, I just do want to emphasize, it's not 5% of the data. It's not 0.5% of the data. It's 0.05% of the data. So very small. You started speaking about the robustness in a model. How can a model be measured as far as robustness is concerned? What features in a model reveal where there's robust or not? So I don't actually see us talking about the robustness of a model. I see us talking about the robustness of a data analysis. And so we have a particular choice of a model. We have a choice of a set of data. And we want to ask, hey, do we think that the big conclusions that we're making from this, and so this is also going to depend on what we count as a conclusion or we count as a decision, do we think that those are going to generalize to other places and other times? And so here's a check that could help us understand if we think that. So, and I would interpret this in the way that you would often in the spirit of a hypothesis test. So if we find that there's a very small fraction of data that you can drop to change your substantive conclusions, well, then we might worry a little bit. And we should probably dig into our data and we should, plot it and figure out what's going on there. If we don't find that there's a very small fraction of data, then, that doesn't mean that there isn't any problem. We just haven't found a problem. About local robustness in the slide and what does it mean? Does it depend only on the signal to noise ratio? So I'm talking specifically here about this robustness that I've described in this talk. Can I drop a very small fraction of data and change my substantive conclusions? And so that's what we're thinking of as robustness. And as I described earlier, again, it's unfortunate that robustness and sensitivity are talked about as though they're monoliths. We always mean robustness to some change, sensitivity to some change. And so that's the change that I'm talking about in this talk. Great, thanks for the questions. Okay, so another thing that one might think is, could I use Bayesian inference or a more complex model and get away from this problem? Maybe in that case, I would always have a robust conclusion. So here we look at actually a paper by our co-author, Rachel Meager from 2022. She does this very cool hierarchical Bayesian analysis of all 7 randomized controlled trials of microcredit. And so I think this is kind of like the best case scenario. She is looking now at not just one data set, but all 7 data sets. So combining all of their information. One of the key ideas of Bayesian analysis, one of the big reasons that people use Bayesian inference is to combine data from sort of different heterogeneous sources. And that's what's happening here. She's combining this data from these 7 randomized controlled trials and seeing what we can conclude from them. She is a Bayesian expert, so she's really taking her time to carefully choose a likelihood and carefully choose a prior. I think it's really the most that we could ever ask for a practitioner using Bayesian data analysis. And even so, even in this case, we can find that we can drop less than 0.03% of the data to change if 0 is in the 95% credible interval. And this is now looking at the microcredit effect across all the countries. So this is coming out of the hierarchical model. And so 0 being in the 95% credible interval, you can think of as a Bayesian form of statistical significance. And here we're basically noting that there's a very strong non-robustness, that we can drop a very small fraction of data and change the substantive conclusion. We can also drop less than 0.1% of data to change the effect sign. So if the decision was based on the effect sign, this is something that we can change as well. And so here we're seeing that being Bayesian isn't a panacea. Just by being Bayesian, you don't avoid this robustness, which I think if you're getting a sense of what this is getting at, that should make sense. You can't just avoid this by using more complex models. We've just been focusing on simple models so far in this talk because we have a lot of intuition about those models, and that gives us a sense of what we're picking up here. Okay, a few more observations. It's not just that everything is non-robust. You might be concerned that, hey, maybe this just picks up that everything is non-robust. Now, technically speaking, we've already seen that not everything is non-robust because we saw that in the simulated example. But you might be concerned that, oh, maybe every real example picks things up as non-robust. And of course, we have kind of a bias of showing you things that are non-robust because we want to show that this is a useful idea. But here, let's see that not everything is non-robust. And so we'll look at the effect of cash transfers on consumption in poor households. In particular, this is from this really cool paper by Angelucci and DeGiorgi 2009 that has over 10,000 data points. We find that you have to drop a lot of data to change any conclusions of this paper. We look at changing the sign of an effect. We look at changing the statistical significance. We look at changing to a statistically significant effect of the opposite sign. In all of these cases, you have to drop 4% of the data, or sometimes I think it's as much as maybe 10% or more. These are cases where we're not even sure that you should trust the approximation anymore. The only thing that we can trust is that there's not a tiny fraction of data that we can drop to change the conclusions. Now, another thing we might wonder is, hey, maybe we're familiar with other types of robustness, and we think that removing outliers is going to save us from this type of robustness. And we're going to see here it's not a panacea. So Angelucci and DeGiorgi 2009, the same paper, also looks at this other very cool idea of a spillover effect. So if some households in a village, the poor households, receive cash transfers, do the non-poor households also in the village benefit from that? So it's a super cool idea. In the original analysis, they are very aware of robustness concerns and hearkening back to sort of the Huber robustness literature, the literature on things like epsilon contamination, they remove the largest responses in a form of trimming. But we can find that even after doing that, we can drop 3 data points out of 4,000, so that's less than 0.1% of the data, and change the statistical significance. How is this possible? In linear regression, the influence score is not just about the response. It's about something to do with the x's as well as the y's, basically. Okay, so something we could be concerned about is, well, maybe those were special cases. Maybe we just got lucky or unlucky, depending on how you look at it, that we had cases where there was good accuracy. So again, in every one of these cases, we did this check that we described of once we have said, here are the data points that we can remove to change the substantive conclusions, let's actually remove them and check that we get what the approximation promised. But you could worry, like, yeah, maybe there are plenty of cases where we don't even come close. And so it's not a good use of our time to run the whole analysis and then find out that it failed. Similarly, I talked about this notion of a signal to noise interpretation, and we saw it for linear regression, but you might ask, is that a general idea? And so let's spend a little time digging into both of these from a theoretical perspective. Okay, on the accuracy side, what we essentially want to say is that our linear approximation, phi super lin, is close to the actual effect of dropping data, phi of w. Well, what does it mean to be close? What's the scale on which to judge this? One potential natural scale is to compare this to the effect of dropping data versus not dropping data at all. We would like this quantity to be large relative to our approximation for dropping data. Well, it's not just that we're comparing these quantities individually for every W. We actually want the worst case over W's because that's what we're finding in this approximation. So we're actually trying to find, hey, what's the worst case W? What's the worst case effect of dropping data? That's what we're reporting. That's the notion of robustness that we've been considering. Okay, so what we show in our theory is that we can bound these two quantities. And in particular, the key point here is C1 and C2 are constants, and we're really looking at the behavior of this alpha versus square root of alpha bound. Now, things are a little bit backwards here because we're thinking of alpha as going to 0. We're thinking of alpha as being very small. And so in particular, when alpha is very small, square root of alpha is going to be larger, and alpha is going to be smaller, a little bit backwards than what you might be familiar with thinking of asymptotics as, say, n goes to infinity. And so the key point here is that under various smoothness and regularity conditions, which are actually quite important, the bound on the error in the linear approximation shrinks faster than the bound on the difference due to dropping data. And we're thinking again here as alpha goes to 0 for very small alpha. Okay, so we might think that there's reason to trust this approximation when you think you trust a Taylor series expansion, basically. Okay, how about the interpretation side? Oh, and this is, of course, there's still important limitations. Again, when you don't trust a Taylor series expansion, you shouldn't trust this. Okay, and on the interpretation side, I said there was this notion of signal to noise. So let's see if we can get a more general notion than just that particular one that we had from linear regression. And so remember, the thing that we're doing at the end of the day is we're saying for this worst case weight vector W, so let's call that W star, have we changed things enough to actually change our conclusion? And so we're comparing this to the amount of change we would have to make to change our conclusion. Let's call that the signal delta. What we show in our theory that we can decompose, so signal, again, is the size of change that would reverse our conclusion. So we show in our theory that we can decompose this right-hand side as a noise term times a shape term. So here the noise is just a consistent estimator of the standard deviation of the limiting distribution of the quantity of interest. We saw an example in that linear regression example. And the shape turns out to be something that basically converges in probability to a non-zero constant. And so two things we get out of this that are nice. One is a notion of signal to noise. Literally, we're taking signal, dividing by noise, and comparing it to something that's roughly a constant. And so truly, we are getting a comparison of signal to noise. We're making our decision. We're seeing the amount of sensitivity that we have based on a signal to noise ratio. And that's exactly the signal to noise ratio. And two, this has important corollaries. So for instance, as n goes to infinity, all of these things are converging to constants. And so the AMIP sensitivity does not vanish. That is in contrast to a normal p-value. If you're looking at a standard error, typically just by getting more data, it's going to go to 0. And so statistical non-significance becomes AMIP non-robust. And if you think about this, I think this is, pretty desirable. You don't want it to be the case, because real life is misspecified, that everything looks perfect and you get a statistically significant result just because you've gotten a ton of data. What if your data is biased? What if there's some issue with your data? What if you know that you have model misspecification, which is always the case, whereas we don't have those issues with the AMIP. Okay, so just to wrap it up, we present a way to check if there's a very small fraction of data that you can drop to change your decisions, an empirical and theoretical analysis of its properties. Our paper is up on the archive. And again, I just really want to emphasize the amazing work of Ryan Giordano and Rachel Meager. Ryan, my postdoc, has code up at his GitHub repo. This is R. Giordano. It's called ZAM influence for Z estimator maximum influence, because again, that's the thing that we are looking at, and it applies to Z estimators in general. I didn't talk about this today, and we don't actually have this in our paper, but a very cool person online who is not us, Michael, made a blog post about how our method can be used to flag p-hacking. And so Ryan, again, has a super cool follow-up blog post talking about why this is, how this is the case, but that I think is a really nice result. And then finally, I'll just mention that reproducibility here is a prerequisite. So I hope nobody would take this as some kind of gotcha for the economics field. Like, I think quite the opposite. This is a real testament to the economics field that we could even run these analyses, that we could reproduce them so perfectly. I think they're way ahead of many other fields. I would assume that any other field would also have sensitivity until proven otherwise. And it's just hard to do that in other fields if we don't have that reproducibility. And so we actually have a paper in 2020 pointing out that there are cases in medical AI where there certainly isn't full reproducibility to check out that you're getting the same results, that you can get the same results as a published paper. And that seems like a really important area where people really care about the results. And so, so some really great work by the first author here. And then we have another paper in Science Advances in 2023 pointing out that really the check that I've just described here is just part of a broader system of checks that we want to be doing on all of our analyses. So again, I want to emphasize this point. This isn't the be-all end-all. It's one check that we think is often going to be useful. And we're just hoping that people use it as part of that broader system of checks. Great. Thank you so much. And I'd be happy to chat some more. Take any questions.
Thank you, Tamara. There is one question in chat already.
Yeah, I see that. It looks like you're creating some type of confounding by dropping some data. Is it correct? I'm not sure I totally followed the question, but it is possible that is true, and I'm just not following the direction of the question. Sorry about that.
So Vinicius, if you feel like explaining a little bit more. Meanwhile, there's some delay between whatever he will see and anyways. I have a few questions because this is very interesting, and this kind of influential analysis, residual analysis, and so on, it has been very strong in statistical setting. Basically you have to verify your assumptions. That was the basic things by then, and then you have this influential thing saying the conclusion was very similar to this. You have a few data points, or it could be due to outliers or many reasons people will try to explain that will drastically change your conclusions, and that might be a problem. Again, you're revisiting this in a more broader perspective in some sense. And I think that's very interesting message that statistics can bring, because my conclusion from your talk is it's very this. If you verify this, what do you do? Because that's the problem, right? So you come up with the Amazon CEO story. Okay, there you have an explanation. Just remove those guys because they affect your village. Okay, that's easy to relate with and follow up. But now I have a data set. I hope everything is just IID in some distribution that it's unknown and so on. I do this kind of complicated modeling to explain things, and I notice that I remove 0.01% of my data, and I get any results I would like. That's basically your, I think, is slide A conclusion. You can change the effects, but my conclusions, because of that, the error is so big, you can go any direction. If you get different subsets, probably you can get positive significance, negative significance, insignificant, or whatever, just by changing a little bit your data sets in a specified way that, and that's dangerous because people, I don't know how you see science there, but I see people doing this, this doesn't look nice. Just remove these outliers. They are just 0.01% of my data set. This is exactly what I expect, and they will move from there. And sometimes they don't even tell us that they removed this. And so what to do?
Yeah. Okay. So just to reiterate the question, which I think is a great one, is what comes next? And I will say some things, but I want to emphasize that our paper does not make a claim about what comes next. And I think that's on purpose. And that's because I think, as you've already laid out, it depends. So if it were the case, for instance, that some of my data is just corrupted, like in the CEO example, like, oh, these people shouldn't have been here in the beginning, or my cat walked on my keyboard and, messed up some of my data points, that's an easy fix. But there are definitely cases where there's not an easy fix. And so maybe let me just illustrate another case. So we talked about this linear regression case in some depth, but I think it helps to sometimes just see what that looks like. So here, so my student Stan is his nickname. Tin Win has done these cool plots on what happens in linear regression case because he's been working on some follow-up work related to this. And so in particular, the observation again is if I have this very low signal to noise, there's no gross outliers here. There's nothing that's a corrupted data point. It's just this issue that when I have a very low signal to noise, I can easily remove a small fraction of the data to change my conclusions. And that's because there's such low signal to noise. So in particular here, if I just have a big blob of data, then the way that I can get a positive effect size is I just remove the corners to get that positive effect. Or if I wanted a negative effect size, I could do the same thing and just remove the corners over here and I would get a negative effect size. And so I think the observation here is first, probably a universal thing that should come out of if you ever detect that there's a very small fraction of data that you can drop to change your conclusions is you should go back and plot the data. And in particular, you should plot like somehow what's different about these data points that you're removing from the data points that you're not. And in this particular case, I would like to think that if somebody plotted this data, they would realize there's not, yes, the p-value might have been very small just because you had a lot of data, but there's not really a substantive, clear effect that's going on here. Again, it's very possible to be sort of like deceived just by having a ton of data because you get these very small standard errors. But we should worry about making really large conclusions that affect a lot of, people's lives based on a plot like this, I think. And so that's the left-hand plot here. This plot is about changing statistical significance. We can make things more or less significant by just removing things at the top and bottom or the sides. But I think the observation here is that it really depends. I do think something that's very, very tough is like when it actually isn't an issue of just, hey, I had these weird data points that snuck into my data set, but I did this big analysis and maybe it's just somewhat inconclusive at the end, or there isn't enough signal to noise to really tease something out. And I think that just can very much happen in science and social science and engineering. And this is partly meant to hopefully defend against that in a broader scientific perspective. And I think also, getting at your question a little bit, I mentioned this p-hacking analysis. P-hacking is something that people can do without being aware of it. They could just run a lot of statistical analyses and then just report the statistically significant ones. And it just turns out that you get sort of a brittle set of results by doing that kind of thing. And so what's cool in this case is this is detecting that there is that brittleness. What's tough is that now you have to follow up on that and say, oh, actually, I wasn't really sure that this was a statistically significant result. Maybe I have to run a reproducibility study, or I have to, check again or change the conditions of my experiment. But I do think that in many of the cases, this will hopefully encourage people to sort of go back to the drawing board, at least plot their data, but maybe even, set up some new experiments afterwards.
Great. So when you run this, basically you're hoping you can find that small subset, and then you'll be more confident to move along and say, it's kind of I reject the null hypothesis. I'll have trouble, and now I'm confident, and you can report that if you can do that finding that you have on one example there, you need to remove 5% of your data to have something different. You're kind of confident that you can move along, right? That's also a good check, anyways, because if you fail, then you have too many things to explore. I don't know how this will, as I say. Okay, reproducibility to my experiment, that involves a lot of money, a lot of control, a lot of things, sometimes in different labs. Well, it's important, but let's see how things move from here. But I like to see this direction. I think we need to think this way because, we need to make things reliable, because otherwise we just find sporadic things that they're kind of making big statements about, just some crazy conclusions that show up. Another question, but that's more technical, is not really technical, but anyways, you have this approximation on Taylor expansion, right? That can go to any F, but some Fs can be really bad behavior.
Yeah,
and
absolutely.
You said, okay, you need to rely on the Taylor expansion in some sense. So were you guys able to come up with some check if my F is reliable to a Taylor expansion or not? Because I'm thinking on protections, right? I'm going to social science. The guy doesn't know what Taylor expansion is, has no idea how to say this F is. He's not capable of answering that question, and he wants to try this, but he kind of assumes this in some point. So there's any check, say, okay, your F is okay to our method. Your F is maybe in a dial point. Just be careful there, or something like that.
Yeah, absolutely. So let me just start by saying some cases where I wouldn't trust this kind of approximation. And so here's an example. If I know that I am dealing with some highly multimodal loss landscape. For instance, I feel like if I had a deep neural net, I would think that this could be the case. Then if I'm making an approximation based on like optimizing for a particular point and then essentially doing some local approximation around that point, then I don't necessarily think that that's going to be picking up anything global. So what's going to happen in that case? Well, we're still going to be able to use our method. We're still going to find some worst case, worst case dropping data based on the local approximation. And at the end of the day, we can check, did we achieve that change? And so any non-robustness that you find from that series of steps is still conclusive. I mean, you drop that data point or that series of data points, you're still getting whatever change you find from that dropping data, but it could be much worse. And so if I'm in the case where I am not sure about this approximation, again, any non-robustness is conclusive, but if I don't find non-robustness, I shouldn't feel super confident about that. Another example would be if I really think that data points could be interacting in some super meaningful way. Well, we're only going to be looking at this approximation of removing one data point at a time. And so if really the influence is only when the two data points are together or three data points are together or something like that, we're not going to capture that in the approximation. And so cases where I might feel more comfortable with this are cases where I think that there could be a good amount of information about globally what's going on based on some local approximation. And so certainly like linear models, generalized linear models, I think very standard tools that don't have this highly multimodal form. Again, anything is conclusive, but we might worry beyond that. Now, that being said, I love the idea of developing, more checks around this. Are there things that you could say like, hey, I know this is going on? I think some really simple ones would just be like, multiple restarts and finding, perhaps, I mean, certainly something you could do in deep learning is if you have multiple restarts and find yourself at different optima, and you do the check based on those optima and see, what do you get there? But that's just going to tell you about those 2 points now. You don't know that there's not a million other potentially like local optima that you might care about as well. So it's definitely a concern.
Okay, I think Vinicius wrote again.
Great, yeah. I see. I mean, when you remove data points using that algorithm, are you truly estimating the same effect that you were estimating before removing them? And so I think this is totally a reasonable concern. For instance, if I have a randomized controlled trial, you might be concerned, like maybe if I remove everybody from one arm of the trial versus not the other arm. But I also think, conversely, maybe an argument for why you might be concerned about this is like that's exactly what could be happening in terms of something like dropping or missingness not at random. It seems totally plausible to me that you could have missingness not at random, for instance, in a healthcare scenario where people are only going to drop, if they're feeling poorly or unfortunately become deceased or, something like that. And so if you are concerned about something like missingness not at random, then I think that this isn't a concern. If you're not, then I don't know. I do think that it's still the case that you're probably concerned that such a small fraction could have such a big effect. But I agree that you might be concerned that it's not quite the same thing. Now, something you can easily do is adapt this framework so that you drop the same amount from each arm. So you could just have like weights so that, you do that. And that would be fine to do. We didn't do that in our particular applications or in like the analyses that we were doing, but it would totally be something that could be explored.
Okay. So Tamara, I think we crossed time a little bit, but that's fine. I would like to thank you again for your wonderful talk and I like this kind of presentation because I know how much theory and work has behind this, and you pass the message smoothly for the students and so on. This way, I think everyone can relate to your talk without the too many details. The details are in the paper, so anyone that's interested, I'm sure you can go there and see all the detailed simulations and so on. Thank you very much. I will just finish the transmission, and I ask you to stay a little bit longer in the studio so I can thank you again. Okay?
Yeah, thanks so much for having me out.
Okay. Let me do this.